So some of the advantages of the feedback control system, as you can see, sensitivity of the system to variation in the parameters of the process. You decrease that sensitivity if some parameters are changing in the system. Then we're going to discuss sensitivity in a little more detail in this chapter. But if some parameters are changing, then you can, in the feedback control system, basically the sensitivity to those changing parameter can become less. So you're not dependent on the change of certain parameter as much as you will be in the open loop system. Improve rejection of the disturbance, external disturbances, basically by improving the signal that is being adjusted to provide the correct output. Improved measurement, noise attenuation, internal noise, and improved reduction of steady state error of the system. Again, if there's a steady state error, that is, let's say input is unit step and the output steady state is 0.5. So now you have an error of 0.5 because input value was 1, output value is 0.5 at a steady state. So the difference is 0.5. That's a steady state error. That what is the difference between the input steady state value minus the output steady state value. Now these two values should be as close to each other as possible, because remember, our input is our desired output, or our input is our desired output. So we want to reduce the steady state error as much as possible. And in the feedback control system, we can do that. And easy control and adjustment of the transient response of the system. We want the transient response to have a specific shape, then we can do that in the feedback control system. So these are some of the major characteristics of the closed loop feedback systems over the open loop systems. We look at the signal flow graph and we looked at the block diagram. So on the left side, you can see the signal flow graph of the block diagram that you see on the right side. Now in this block diagram, you have three signals. You have the desired output, which is RS, you have the external disturbance, and you have the internal noise. So you can see all three signals in this block diagram. And when you convert that into the signal flow graph, then you have the signals given as the nodes, of course. You have RS, you have NS, you have TDS, and then you have YS, and then you have the branches, and the weight of those branches are the transfer function in the block diagram. When you write down the output of this in terms of RS, TDS, and NS. Now we already did in terms of RS and TDS in the last chapter using superposition. If you extend the superposition for RNS as well, then your complete equation is going to be this. So in the last chapter, we did the first two parts, these two. And again, if you further extend it and assume that only N is active in the system, and assume TDS and RS to be 0, and then apply whatever method that I showed you about following the signal, then the relationship between YS and NS is going to be YS is equal to negative GCS GS over 1 plus GCS GS times NS. And you must do the derivation to show that this is what you're going to get. I'm not doing it at this time because it's the same derivation basically that I did in the last chapter for RS and TDS. Now you have NS as well. So you can make RS 0, TDS 0, and then do the derivation for NS as what will be the YS if you have only NS in the circuit, in the system. But this is the complete expression if you have all three quantities, RS, external disturbance, and internal noise. We define what is the error between the output and the input as the tracking error. So the error between the output and the input is the tracking error. And this is what we want to reduce as much as possible. So if we take that, ES is equal to RS minus YS, And ys expression is that, so we plug that ys expression over there. Then the expression for es is going to come out to be this. You can have rs minus this, which is gcs gs over 1 plus gcs gs rs. And here we are assuming we have a unity feedback system, so we are assuming that h is equal to 1. That's why you don't see h here in this expression. We are assuming that it's a unity feedback system, so h is 1. So when you write down the expression for the tracking error by substituting y sub s here, then you're going to get this expression. Now we define different terms in this expression. Include first the loop gain. Loop gain is GCS GS. What is the loop gain? Again, it's the gain of the loop. You have one loop, and the gain of that loop is GCS, GS, and HS is 1, of course. So GCS, GS. And loop gain is an important parameter in control systems. And wherever you have GCS, GS, you can replace that by the loop gain, L. So all those GCS, GS are replaced by L, LS, LS, LS. So all these are GCS, GS. And in NS, you have GCS, GS on top as well. Then we define what is the sensitivity of the system. Sensitivity of the system, which is the measure of the amount of change in the system's output with respect to the change in any of the system's parameter. That is defined as the sensitivity of the system with respect to that parameter. And that's an undesired change in any system parameter, basically. So sensitivity of the system is defined by 1 over 1 plus LS. Why? We're going to come back to this why. And you will see that this equation is going to turn out to be the sensitivity equation when we discuss that later on. But right now, we are defining sensitivity of the system as 1 over 1 plus the loop gain, 1 over 1 plus GCS GS. This is 1 over 1 plus GCS GS. Again, we're going to come back to this to show you why the sensitivity is defined by this expression. And then we also define complementary sensitivity of the system, which is LS over 1 plus LS, or in other words, GCS GS over 1 plus GCS GS. So that's the complementary sensitivity. Why it is complementary? Because if you add sensitivity and complementary sensitivity, your result is 1. So sensitivity is 1 minus complementary sensitivity of the system. So all these terms we are defining right now. And using all those terms, we can write down the expression for the tracking error to be sensitivity of the systems times R of S, go back, 1 over 1 plus GCS GS, that's the sensitivity of the system, 1 over 1 plus GCS GS. So error is sensitivity of the systems times RS minus sensitivity of the systems times GS TDS, GS over 1 plus GCS GS. This is the sensitivity of the system, 1 over 1 plus GCS GS. So sensitivity of the systems times GS times TDS. Oh, right here, this one. And finally, complementary sensitivity of the system times N of S. This is the complementary sensitivity of the system times N of S. Complementary is GCS GS over 1 plus GCS. So we write this equation down in terms of sensitivity and complementary sensitivity. And you also have your transfer function of the process, GS. GS is the transfer function of the process that is being controlled. So that's your error equation. in terms of sensitivity, input signal, complementary sensitivity, process gain, and of course TDS and NS. So what do we see from this signal? 4.8 equation. Few things that we observe. Observe that for any process GS, to reduce the tracking, this is tracking error, not tracing error, tracking error. To reduce the tracking error, both the sensitivity and the complementary sensitivity need to be reduced. Both S and C, if they are smaller, then of course error is going to be small. But it's not possible because they are complement of each other. One is increasing, one is going to decrease. As we see over here, SS is 1 minus CS. If CS is reducing, SS is increasing. If CS is increasing, SS is reducing. So both of them cannot become small at the same time. So what do we do? However, from 4.7, it can be observed that both SS and CS cannot be reduced simultaneously. So from 4.4 right here, from 4.4, we see that reduce the effect of disturbance on tracking error, loop gain needs to be large over the frequencies of disturbance signal. So to reduce the effect of disturbance error, this is disturbance, LS needs to be large because it's in the denominator. And remember, the system is working at different frequencies. At some frequencies, you will have higher amount of disturbance. At some frequencies, you have higher amount of noise. So we have to look at what frequencies we have to reduce the value of the loop gain, we have to reduce the value of the complementary sensitivity and all those things. So to reduce the effect of TDS on the error, the denominator has to be increased. And the denominator is going to increase when LS is going to go high. The loop gain is going to become larger. And that's what it's explained here. We see to reduce the effect of disturbance, loop gain needs to be large over the frequencies of the disturbance signals. To increase the loop gain, gain of the controller for a given process need to be increased because gain of the controller and GS is product of that is LS. So if your GS is not changing, gain of the controller has to be increased in order to reduce the effect of TDS. On the other hand, to attenuate the effect of measurement noise, loop gain needs to be reduced to reduce the magnitude of the transfer function associated with the noise. So go back. You have to reduce the numerator LS in order to reduce that factor or effect of that factor on the error signal. The numerator has to be reduced. That is, loop gain has to be reduced. So in one case, we have to increase the loop gain, and in the other case, we have to reduce the loop gain. Increase the loop gain to reduce the effect of the disturbance, and increase the loop gain to reduce the effect of disturbance, and reduce the loop gain to cancel the effect of noise. Now, we cannot really do the same, reduce and increase at the same time. So again, go back. To attenuate the effect of measurement noise, loop gain needs to be reduced to reduce the magnitude of the transfer function associated with the noise. This means the controller gain must be reduced in order to reduce the effect. So the control engineer basically has to do all those things. Control engineer must create a design such that at lower frequencies, gain of the controller must be high, since external disturbance is predominantly at lower frequencies, and at higher frequencies, where noise is more pronounced, controller gain should be smaller. So the good thing is that these two inputs, external disturbance and internal noise, they have their own frequency band. So you are creating a controller to control the process such that that controller gain is larger at one set of frequencies to reject the effect of the noise or disturbance, or is smaller at other set of frequencies. So like, you read it here, must create a design such that at lower frequencies, controller gain will be high. And at higher frequencies, controller gain will be low. So what type of system is that where you have high gain at low frequencies and low gain at high frequency? It's a low pass type of filter, low pass type of system. So if you create GCS such that it acts as a low pass type of filter, then you can have you will successfully be able to reduce the effect of both TDS and NS on the input signal. So let's write this. A low pass type system. Okay. All right, what time it is? 4:25. Let's see what else we have to do. Sensitivity. Some example. I don't know. All right, let's go ahead and then I guess we can stop here. I think we are running a little behind, but it is what it is, I guess. So let's go ahead and stop here and then start from this point next week from the sensitivity of the system, how to calculate the sensitivity of the system. So basically we just discussed some theory. We didn't do any problem from chapter 4 so far. It's just some theory. So there is no problem that I'm going to be assigning from chapter 4 yet. So the problems that I will be assigning are there from chapter 2. Basically block diagram and signal flow graph. And that's what the quiz is going to be next week. So we'll stop here and continue from this point on next week.